So let's talk a little bit about a limit. When you are finding a limit of a function, you are finding what y is approaching as x approaches a certain value. And what's important here is the word approaching. So what is y approaching as x approaches a certain value? And I'll talk about here what I'm evaluating a function in just a second. Okay, so let's hold on that. What is y approaching as x is approaching a certain value? So let's take a look at a graph. If we want to take a look at the limit as x is approaching -1. So the way we would write that is the limit as x approaches -1, okay, of this function. And we're going to go ahead and call this function f of x. So this is the function f of x. All right. Okay, so what is the limit as x approaches -1 of f of x? What is that? So in order to find the limit as x approaches 1 of negative x, we need to take the limit as x approaches -1 from the left and from the right of the function. Let's analyze. So we're going to get on the function, and we're going to come at the function from the left-hand side. Let's jump on, and nope, and we're trying to get to x -1. All right, here's x -1. So about, there we are. And as x is approaching -1 from the left-hand side, so x is approaching -1 from the left-hand side, what is y approaching? Okay, as x is approaching -1 from the left-hand side, y is approaching 4. Y is getting closer and closer to 4. Here we have a y value of 2, 2.1, 3, and so on and so forth, all the way till we get to 4. Now let's take a look at x is approaching -1 from the right-hand side of the function. So we jump on the function on the right. Let me get a better, here we go. We jump on the function from the right, and we're coming over to -1. We're still not there yet, still not there yet. Here we are. Okay, so it's also approaching 4. Y is also approaching 4 as x is approaching -1 from the right-hand side. Okay, so since the limit from the left agreed with the limit from the right, as x is approaching -1 on this function from the left and the right, y is approaching 4. All right. Now, I don't know how far you know or what notation you know, but the way this is all written is we went ahead and we looked at the limit as x approaches -1 from the left. And that's what that little minus sign up there signifies, from the left. When we looked at the limit as x approaches -1 from the left, that was equal to 4. And then we looked at the limit as x approaches -1 from the right. That's what that means, from the right. That was when we came at the graph in this direction. And as x was approaching -1 from the right, y on the function was approaching 4. Okay, so that approached 4. And since the left and the right both agreed, the answers were the same, then the limit as x approaches -1 exists, and it is 4, which means that as x approaches -1 on the function on both sides, as you're coming to -1 off on the function on both sides, y is approaching 4. So the limit exists. Also, since the limit exists, and since the right limit and the left limit, the right limit and the left limit are the same, okay, then that means that f of x has to be continuous at x equals -1, which means there's no holes or breaks in the graph at x equals -1, which is true. Right at x equals -1, I have continuity. I was able to smoothly go through the function at -1 without jumping or breaks or a hole or anything like that. So look at how this all ties in together. Since the limit as x approaches -1 from the left equaled the same answer as from the right, then the limit existed, which tells me, since the limit exists, that it is continuous at x equals -1. Okay, now the vice versa is true. If f of x is continuous at x equals -1, then the limit must exist. So if I didn't have this graph, if you didn't show me that picture, okay, but you told me, let's see here, if you didn't show me this picture, but you told me that the function was continuous at -1, then I would know that the limit at -1 exists. Okay, so since the limit exists, the function is continuous. Since the function is continuous, the limit exists. Now we're only talking about at -1 because you could tell real quickly that this function is not continuous everywhere. There's a break right here, there's a break right here, and there's a hole right there. So this function is not continuous everywhere, but at x equals -1, it is continuous. The limit at x is, as x approaches -1 of f of x is 4, which means that f of -1 must equal 4. Isn't that true? Okay, so when you are evaluating a function, f of -1, you are finding what is y when x is a certain value. So when I ask you what is f of -1, I'm asking you what is y when x is -1. And in this graph, it's 4, which is the same answer, okay, as the limit. Why? Because it is continuous. Since the function is continuous at x equals -1, the limit value, so the limit, what y is getting close to as x is getting close to, so as x is getting close to -1, y is getting close to 4, that value and this value are the same in continuous functions. Makes sense because y is approaching 4 from the left and the right. Y is approaching 4 as x is approaching -1. Well, hello, when x is -1, y is straight up 4. So that's the whole deal with limits and continuity. So let's take a look at a discontinuous situation. So now let's let's find a place where the graph is discontinuous. And it looks like it's discontinuous right here at -4. So let's take a look at the question, what is the limit as x approaches -4 of this function, f of x? Okay, what is that equal to? Again, this is function f of x. This is function f. I don't know why my pen is not working. Okay, let me try that again. This is, call this f of x. Okay, so as x approaches -4, what is y approaching? So as x approaches -4, what is y approaching? So in order to answer this question, I have to look at f of x coming at -4 from the left and from the right. So let's check the left and the right. So first let's do the left. What is the limit as x approaches -4 from the left of f of x? Let's analyze that first. And then we'll analyze the limit as x approaches -4 from the right of f of x and see if they agree, because if they agree, then the limit exists. All right? So let's jump on f of x on the left. So this is the left side, so let's jump on the function. Jump on, and let's approach -4 for x. So we're at -6, -5, here is -4. So as x is approaching -4, y is approaching 3. So it's going up to 4, coming down, and at 3. So that's as x is approaching -4 from the left, y is approaching 3. Let's write that down. Okay. Now let's jump on the graph on the right-hand side, because we're going to approach -4 from the right. Now I'm going to be dramatic here and jump all the way over here, but we know we can come over here. I'm going to jump all the way to the right and get over to -4. Still not there, still not there. Oh, I'm getting closer, closer, closer. Slow down. As x is approaching -4 from the right, y is approaching -2. Okay. Now, do the left and right limits agree with each other? Does the left limit agree with the right? No, it does not. So what is the limit as x approaches -4? Okay, so as x is getting closer to -4, what is y getting closer to? I don't know. Is it this one? Is it this one? Is it this one? Is it this one? There's no way to know. The function is discontinuous there because as x is coming at -4 from the left, it's coming to 3. Y is getting closer to 3, but you're coming at it from the right. Y is getting closer to -2. I mean, the limit does not exist. Okay? It does not exist because is it 3 or is it -2? I don't know. I need one answer. I need one value that y is approaching as x is approaching a certain value, and I don't have one. All right? It really depends, and I can't answer that question. It just depends. Okay, so the limit does not exist. So you can see here visually that the function is discontinuous. F of x is discontinuous at x equals -4. It has a jump discontinuity at x equals -4, right? But what is f of -4? Well, f of -4, that's a completely different question than the questions we were looking at below. F of -4 is that ordered pair right there. F of -4 is 3. So that has nothing to do, this has nothing to do with any of this. Because before, in the last one, this value was equal to this value because it was continuous, right? But in this problem, it's discontinuous. Well, there's still an ordered pair here, but it's not the same as the limit value. Well, why? Because there is no limit value. Well, why? Because the function is discontinuous at x equals -4. It's discontinuous because the limit as x approaches -4 from the left is not equal to the limit as x approaches -4 from the right. That's going to happen again here. And that's going to happen again as you approach. It's going to happen as x approaches 2, and it's going to happen again as x approaches 4, this discontinuity. Okay? And that's very different than this question. This question is saying, what is y when x is -4? So, like, what is f of 4, let's say? Let's say f of 4. Well, f of 4, there is no point there. F of 4 does not exist. F of 2 exists, f of -1 exists, f of 4 does not exist. So that's a little information about limits and continuity. So let's take a look at the questions you guys sent me. So here we're going to find the value of k that makes the function continuous. Okay, if the function is continuous, if f of x, it's f of x, okay, is continuous, then the limit as x approaches some number from the left is equal to the limit as x approaches some number from the right. The limit exists because when you came at, if it's continuous, remember that when you're coming at the number from the left, it's going to be the same. The y value is going to be the same as if you come at it from the right. So if we need to take a look at this picture again to review that, remember that x was continuous. In this case, x was continuous, f of x was continuous at -1 because the limit as x approaches -1 from the left and the right were the same. We're both equal to 4. Okay? So let's take a look at this piece. And this is a piecewise function. This is the graph of a piecewise function. So let's take a look at this piecewise function that you have here. So f of x is equal to the square root of kx when x is between 0 and 5. And f of x is equal to x plus 3 when x is between 5 and 10. Okay? So this 5 is the breaking point. This graph could be continuous or it could be discontinuous. It could be like something like this up to like, oh, it's from 0 to 5. So let's say 0 to 5. So let's cut that off. So let's say that's x equals 5. So it could be 0 to 5 could be like that. This graph could be like this, and then this line could be like that, which makes it discontinuous because there's that hole there. Or the line could be up here, which still makes it discontinuous because there's that hole there. So what value for k, because k is not the variable, x is the variable. K is a placeholder right now for some random number. What value for k will make that line kind of fit right where the other graph ends? So basically, we want this piece of the function, this bottom piece, to start where this top piece stops. We want the limit as x approaches 5 from the left to be equal to the limit as x approaches 5 from the right. So with all that being said, we basically want the square root of kx to equal x plus 3 when x is 5. We want, oh, there we go. We want this piece, this y value, to equal this y value when x is 5 at that breaking point. Because if those y values are different, then the limit won't exist, as you can see from this broken graph over here. But when those y values are the same from the one piece to the other piece, the limit does exist. So we want square root of kx to equal x plus 3 when x is 5. So let's go ahead and do that. So square root of 5k, as I plugged in, x equals 5, is equal to 8. Because again, I plugged in x equals 5 right here and here. And then we can do the algebra to finish the job. 5k is equal to 64, because I squared both sides. And then k is equal to 64 over 5. Yep. And that k value in that function, if you graph this in a calculator or on Desmos, if you graphed square root of kx, or square root of 64 over 5x from 0 to 5, and then 8 from 5 to 10, you would get, yeah, you would get the same answer. So let's check that. Let's do, whoa, hold on. Let's do f of 5. F of 5, yeah, because we want the y value, square root of kx, to be equal to x plus 3 when x is 5. So let's plug 5 in and make sure we did this right. So f of 5 is equal to, okay, so 5. So square root of 64 over 5x. Hold on. I messed up here. Let's put f of x. Let's write our function now. Now that we know k, let's actually write what the function is. That's equal to x plus 3. That's from 0 less than or equal to x less than or equal to 5. And this is from 5 less than x less than or equal to 10. Okay. All right, if we plug 5 in right here, you're going to get the 5's to cancel, and then you'll get 8. If you plug 5 in right here, you're going to get 5 plus 3, you're going to get 8. This y value is equal to this y value at that breaking point of 5. So now they meet, which means the function is continuous, which means that the limit as x approaches 5 of this function has got to be 8. Because when 5, you're getting close to 5, close to x equals 5, this guy's going to become 8. Plug in 5, you'll see. And when you get close to 5, this guy's going to become 8. All right, last one. For this one, I went ahead and graphed it, but let's say you didn't graph it. For any discontinuities, that's going to happen wherever the function is not defined. And since this is a rational function, and I take a look at that denominator, I'm basically looking for values, what x values are going to make that denominator 0. And it is x squared plus 4. So in the denominator. So x squared, that's always going to be positive no matter what. Even if you put a negative number in there, that's always going to be positive. Then you're going to add 4. So it's always going to be positive. So this will never be 0. Actually, this will even never be negative. Because no matter what you put here, you square it, it's going to turn positive. Then you're making it bigger by 4. So there's no way that denominator will ever be 0. So I don't have to worry about that. Okay, so it's not going to be discontinuous anywhere at all. This is always going to be a pretty number down here, and 8's always going to be a pretty number up there, so that's always going to be continuous. And I graphed it so that you could see, but you can graph it as well on Desmos. So here's the graph of 8 over x squared plus 4, and you see that it is continuous, and it just keeps going. So what if it was 8 over x squared minus 4. So if it was 8 over x squared minus 4, then we would have a problem. If you factor that denominator, you'll see that there are two values that will make the denominator 0. You'll have a problem where x cannot be 2 and x cannot be negative 2 on that function. And those would be called jump discontinuities. I'm not quite sure. No, maybe they're not. Maybe they're infinite. I'm not sure what the vocab here is on this one. Let me look this up. All right, no. This would not be a jump discontinuity because this isn't a piecewise function. This would be an infinite discontinuity because these are going to be vertical asymptotes, and it's discontinuous at x equals 2 and negative 2. So there'll be these vertical asymptotes there, so that discontinuity is infinite. It's forever at x equals 2. It's not just at, like, that one picture that we had where it was here and then it went like that. That was jump discontinuity, so it's just jumping at that one point, as opposed to, like, it straight up never will be 2 or negative 2. So it has infinite discontinuity at 2 and negative 2, 2 and negative 2. Jump discontinuity would look like a piecewise function where at that number, at that x value, the y's are disagreeing. Okay, you'll have a y value that's larger than the other, so that's jump. Removable would be a hole also, like in the graph that I showed you at the beginning, where you had the function, let's say that was over here, but it had a hole in it, and it kept going. Okay, that's removable, and that happens when you say, let's say we had the function 8x plus 2, like this, over x squared minus 4, right? I'd say that was the function. Well, the denominator, once you factor it, okay, these will cancel, right? So that discontinuity got removed. So that will make a hole in the graph. That is like kind of like, oh, a hole, and then you just keep going. So this is removable discontinuity at x equals negative 2 and would have infinite discontinuity at x equals 2. And I'm not sure what other discontinuities means. I would have to see your book to understand what that particular vocab term means. But these are, there's jump. This is and jump would look like a piecewise function, like I said, where if you plugged in an x value, you would see two different y values, one for one piece, one for the other. Removable got removed by factoring, which results in a hole, and infinite are your vertical asymptotes. So I hope that helps. All right, bye.